Good evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my next training video in my summer training video series. And this one is going to be on energy, heat transfer, and the seasons. There's a lot going on this opening picture here to start this training. Look at all the different things that we have going on, okay? So we're going to talk about these. These are heat transfer mechanisms. You know, we have this match, it's lit, you see the flame on the end of the match, and you see these arrows representing that heated air rising motion in the vertical. That's known as convection. And then you have some of this heat energy just kind of working off of the flame and moving more horizontally. That is known as radiation. And then we have, you know, the gentleman's finger here, he's holding the lit match. There's a certain level of vibration along this match with the molecules, and eventually, you know, if you touch a metal object specifically, conduction is going to result in a much quicker moving, faster vibrating molecules down this structure down to his finger, and he's going to probably drop it because it's going to be hot. We'll talk more about conduction. This is heating by contact. But we have all these different air motions in the atmosphere that we can relate to these various heat transfer mechanisms. We'll get into it some more. You know, hot air rising, cooler air sinking. So let's get right into the training. We're going to start with a talk of energy. We'll talk about the conservation of energy as well. First of all, let's talk about the two main types of energy. When we talk about the atmosphere as a whole, we have potential energy. Now this is represented by the letters PE, potential energy. And the equation for it is pretty simple. Potential energy is equal to the mass of an object times the gravity times the height. Now gravity is typically a constant always at 9.8 meters per second squared. So if you were to drop a ball, let's say, from the top of a building, that ball is going to fall under the force of gravity at 9.8 meters per second squared. It never changes. So gravity is usually one of those constants. All right, so potential energy, what exactly is it? It's the total amount of energy stored in an object. And it really determines how much work an object is able to do. And the mass of that object plus the height of that object are going to have a big role in how much potential energy or how much work an object is able to do. So the relationship, when we look at this equation, mass times gravity times height for potential energy, you increase the mass, this lowercase m is the mass, that's going to be equal to an increased potential energy. So increased mass, you have an increase in potential energy. Assuming the height is held constant. So we're not varying the height. If we increase the height, that is also equal to increased potential energy. There's a direct proportional relationship here. And that assumes that the mass is held constant. So we said gravity is always held constant. And the mass, in this case, held constant. So there's a direct relationship between potential energy and height. In other words, if I increase the height or hold something higher above the surface, it's going to have the potential to do much more work, and it's going to have a lot more potential energy the higher I hold the object. So an example of this would be a brick. Imagine that you're holding a brick and you only bring it just above your foot. You hold it just above your foot, okay? Compared to if I now hold the brick up at my eye level. If I drop either of those bricks, the brick at the higher elevation or the higher height above the ground at my eye level is going to have the ability to do much more work as compared to that brick held at a lower position. Additionally, we need to talk about kinetic energy. Now, kinetic energy is abbreviated with the initials KE, and it's equal to 1/2 the mass times the velocity squared. Now, the energy of motion is what kinetic energy is all about. Faster motion because it results in greater kinetic energy. Think about when you have a strong breeze versus a light breeze. That stronger breeze is going to have much greater potential, I almost said it. Strong breeze is going to have much greater kinetic energy of motion, not potential energy. I was going there, but that wasn't the case. Really, kinetic energy or energy of motion depends on the object's mass, which we see in the equation, m. When equal volumes of air and water move at the same speed, the water is going to have a greater mass and greater kinetic energy. So you kind of see this mass and kinetic energy are directly related as well. So if I increase mass, I increase kinetic energy. If I decrease mass, I decrease kinetic energy. This movement or motion of molecules and matter is often referred to as heat energy. We talked about potential energy, we talked about kinetic energy. Now let's talk about the conservation of energy. Energy takes many forms and can change from one form to another. For example, we can actually change energy forms from potential to kinetic. Total amount of energy is never going to change, by the way. Energy cannot be created or destroyed. And one of the bigger talks when we talk about the weather and the atmosphere, what type of energy we're most interested in is that solar energy, the sun's energy, that radiant energy. Now, if I were to have the sun's energy or that radiant energy, the sunlight shining on a lake, there's going to be energy that's going to heat the lake from the sun. It's going to cause an increase in the water's kinetic energy through an increase in the molecular motion. The molecules are moving much more quickly when you have an increase in the water's kinetic energy. Now, what happens when you get so much energy and so much motion? You have what's known as evaporation, where work is then being done on the water, and soon this moist air is going to rise and form a cloud. So we're evaporating the water in liquid form, we're turning it into a vapor, the air rises and a cloud forms. So that energy, when the cloud forms, is now basically converted into a process where we take the vapor, the water vapor, and turn it back to a liquid, and this is known as condensation. The cloud now possesses potential energy that will become kinetic energy when it starts to rain, this falling raindrops. So I just want to kind of show you an example of how the energy is changing forms from one to another. Here are some of the main heat transfer mechanisms now we're going to talk about. We're going to talk about solar energy. That's, a form of radiation. We're going to talk about conduction, which is direct contact with something. We're going to talk about wind and the process of advection. And then we'll talk about convection, rising air motion, which we see the visible manifestation of convection in the form of these tower billowing cumulus clouds on a hot summer day. But let's get into these. Right, so the first heat transfer mechanism we'll talk about is solar radiation. Now, heat transferred by radiation is simply the sun's rays hitting the Earth. The Earth is going to maintain a balance by holding some of that solar radiation and then also throwing some of that radiation back out to space. Latitude and the land-water distribution, which we talked about in the previous training video, they play a big part in determining the amount of incoming solar radiation and those temperatures. What about the next heat transfer mechanism, conduction? All right, we can do an example of conduction by just simply, if you were to hold one end of a pin and place it over a flame, the energy absorbed by the pin will then turn into molecular motion, vibrating molecules along the pin. And this is going to result in the metal beginning to get hot. When you increase the molecular motion, you're increasing the temperature of that substance or object. So the increasing temperature increases the molecular motion. Those molecules move quicker and quicker, and the molecules in the pin then begin to vibrate faster. They collide with neighboring molecules, and with time, the molecules in your finger are going to be affected, and the pin just simply becomes too hot to hold in this case. This heat transfer process via direct contact is called conduction. Here is some of the examples here. So again, if you're holding this pin over this open candle flame, right? The molecules again along this pin are moving faster and faster, and they're colliding with neighboring molecules. With time, this molecular motion increases so much that the temperature of this pin heats up so much that it works its way down the pin to your finger, and you're simply going to drop it because it's going to be too hot. It'll burn your skin. Additionally, if we look at conduction, we can use the analogy when you're cooking in the kitchen, where you're heating up a pan of water on the stove, and that acts in the same manner as the pin we just covered. Eventually, this handle may become too hot to touch over time. Now, the solids or metals generally are good conductors of heat. Transfer is always going to occur from warm to cold. By the way, air is a poor conductor of heat as compared to the solids and metals. So if we were looking at the atmosphere with a calm wind on any particular day, let's say the sun's out heating the ground, that hot ground is only going to warm a shallow layer of air a few inches thick. That's because air is such a poor conductor of heat. So its conduction is going to be limited to a very shallow layer near the Earth's surface. And conduction is a very important process in that it sets up other heat transfer mechanisms or methods, such as convection and advection. And we're going to get into those here right now. Convection is simply the vertical transport, it's usually upward, of air. It's called free convection when the surface warms via that direct contact conduction we just talked about. It's called forced convection when there is some other lifting mechanism involved, such as a weather front, a cold or a warm front, orographic lifting caused by mountains, or low-level convergence. Advection, on the other hand, this is a big form of heat transfer, especially in the winter season. It's a horizontal transfer of heat via the wind. That's what advection is. So think horizontal transport of heat. And the wind is the primary way in which this advection occurs. And again, it primarily occurs in the winter season when there's large temperature gradients or large temperature changes across the latitudes. Here's an example. So on a cold winter day, on a heart of winter, a day may feature in January a temperature of 70 in New Orleans, but it might be -10 up in northern Minnesota. That's a large temperature gradient across those latitudes. So the atmosphere gets really smart and creates storms, low pressure systems, and those storms really allow for warmer air to move north, colder air to move south, and that is advection. And just keep in mind, the stronger the wind speed, the stronger the temperature advection is going to be. Temperature advection is usually very weak in the summer season, and it's very strong in the winter season. You're having temperature advection when, let's say, you have a temperature in, let's say, the lower 60s one day, and then the next day they're only in the 30s. With that cold front coming through, there was a change from warm air advection to cold air advection over 24 hours. Things happen rather dynamically in the winter season. The weaker the wind speed, and that's typically the summer, we just don't have that large temperature gradient across the latitudes in summer, so you have weaker temperature advection. Right, now I wanted to kind of go over the seasons, and we'll take a look at the Earth-Sun relationship to conclude this training video. All right, so here's our schematic at the top, our diagram. So I'm showing you various times throughout the year at which the Earth is revolving around the Sun. So it takes 365.25 days for the Earth to make one complete revolution around the Sun. Now this orbit is not completely circular. If it were more circular around the Sun, we'd have a drastic change to our temperatures and our seasons. The revolution of this Earth around the Sun is only a partial reason for our change in seasons. The primary reason is going to be the Earth's tilt on its axis, which I kind of alluded to in the last training video. So let's go through this. Main reason we have our seasons is the Earth's 23.5-degree tilt on its axis. So you notice this diagram on the right kind of showing you that 23.5-degree tilt. This would be 90 degrees straight up and down, right? So 23.5 degrees off that 90-degree tilt, or a 23.5-degree tilt. This automatically or drastically changes the amount of sunlight striking the surface and how long the sun shines at any latitudes. How many daylight hours are there at various latitudes? This tilt is really going to dictate that. Now radiation hits the surface. When it hits the surface at a high sun angle, you're going to get more of a perpendicular component to the solar radiation to the surface, much more intense radiation striking the surface as compared to sun at a low sun angle just slightly above the horizon, which is going to be much weaker radiation. So low sun angle radiation is going to spread out over that larger area. It's less intense. Longer daylight hours also mean more incoming solar radiation. So during the summer season, we get a lot more daylight hours, which means we have a lot more sunlight, which results in more incoming solar radiation. Now let's just break down the various benchmarks of the seasons. We'll start with the summer solstice. Now this occurs at the beginning of, this is considered the beginning of summer for the northern hemisphere, falling on or around the 22nd of June. In the northern hemisphere, we are tilted towards the sun on the summer solstice. And at noon on this day, the sun is going to be at its highest point in the sky over us. And it's going to be most directly over the Tropic of Cancer on the summer solstice at 23.5 degrees north latitude. And even though we are farthest from the sun on around 4 July, the sun angle is still more intense. It's more perpendicular to the surface of the northern hemisphere. So that's going to keep the temperatures very warm in the summer. Even though we're farthest from the sun, the Earth's relationship to the sun, the Earth is farthest from the sun in early July. It doesn't matter because that sun angle is just so direct and so much more perpendicular. Now, over here on the right, I'm showing you an example of how the sun makes its path across the sky around June 22nd, the summer solstice. The sun generally is going to rise in the northeast. It's going to go up really high in the sky, about 180 degrees towards the south. It's going to reach its highest point in the sky, and then it's going to slowly descend into setting in the northwestern portion of the sky. So the sun generally around the summer solstice, it rises in the northeast and sets in the northwest. And it has its longest path or trajectory overhead across the sky. The winter solstice, on the other hand, now this is the beginning of winter for the northern hemisphere. It falls on or around the 22nd of December. This is a case where we, the northern hemisphere, are tilted away from the sun. Daylight hours are very short and nights are very long. So you'll notice this easily in late December. You don't get much daylight and the nights are pretty long. Sun is directly over the Tropic of Capricorn at 23.5 degrees south latitude at the winter solstice. And the noonday sun is now at its lowest point in the noon sky. And there's actually complete darkness for 6 months at the North Pole during this time period. And then despite being closest to the sun in early January, the sun angle is so low, just above the horizon, we're still going to have colder temperatures. Here's my diagram on the right. So look at the difference here. December 22nd, winter solstice. The path is much shorter, number one, from sunrise to sunset. The sunrise is going to occur in the southeast, and it's going to set in the southwest. But this is much less direct solar radiation at this point. Shortest path in the sky. Now on to the autumnal equinox. This is the official beginning of autumn or fall for the northern hemisphere. It falls on or around the 23rd of September. And day and night are of equal length across the entire Earth, about 12 hours a day and 12 hours a night at the autumnal equinox. The sun is going to be directly over the equator at 0 degrees latitude, and the daylight hours generally become shorter in the northern hemispheres with this date. And so what happens at the equinox, it can be either spring or fall. The sun is going to rise directly in the east at about 090 degrees and set directly in the west at 270 degrees. So that is the big difference in the path of the sun across the sky. Rises directly in the east, sets directly in the west. And then finally we have the vernal equinox, or the spring equinox. This is the official beginning of spring for the northern hemisphere. It falls on or around 21 March. And again, day and night are of equal length. So we have 12 hours a day and 12 hours a night across the entire Earth. The sun is directly over the equator once more, similar to the autumnal equinox at 0 degrees latitude. And the daylight hours are becoming longer in the northern hemisphere the first day of spring. We're starting to see more direct incoming solar radiation and longer days, and that generally relates to warmer temperatures. And again, just like the fall equinox, the spring equinox, or vernal equinox, the sun is going to rise directly in the east and set directly in the west. All right, that wraps up my video. We talked about types of energy. We talked about the conservation of energy. We talked about various heat transfer mechanisms that we see in the atmosphere from solar radiation. We have incoming solar radiation, but we also have outgoing long-wave Earth radiation. So both the sun and the Earth emit radiation of some sort, short and long-wave radiation. Then we talked about conduction, heating by direct contact. Air is a poor conductor of heat, so only a very shallow layer near the Earth's surface is actually heated. We talked about how if we heat an object, if you hold, for example, this pin over the flame of a candle, that energy, the molecule is going to vibrate, move faster, and the energy is going to result in increased energy and molecular motion. it's going to result in an increase in temperature, and eventually it's going to be too hot to hold over the flame, and you're going to probably drop this pin. Similar to a pan cooking on a stove, boiling water as an example. And then we talked about convection and then advection and the Earth-Sun relationship to seasons, as well as what's the main reason for the seasons and the various benchmark dates that we utilize to classify seasons. Summer solstice, we looked at the winter solstice, we looked at the autumnal and the vernal or spring equinox. All right, everybody, I hope you enjoyed this presentation, and hopefully you understand things a little bit more clearer. And I've got more training videos ahead, so stay tuned for that here on the Spot On Weather YouTube channel. Thanks so much for subscribing to my channel, and looking forward to some more training. I hope you're having a great summer so far, and that's all I got for now. Take care and God bless everyone.